Good day and welcome back for part 2 of our discussion on the definite integral. And before jumping into the example we would like to investigate in this current video, let me give you a quick reminder of how we define the definite integral and its interpretation. So recall that we said the definite integral of a function f of x from a to b is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x, where the quantities delta x is defined to be b minus a over n, and x sub I is a plus I delta x. Hopefully these are becoming quicker and easier for us to recall. And the interpretation is that this is very similar to what we previously discussed with calculating enclosed areas. And in fact, it is most definitely telling us something about enclosed areas, but it's really a net difference of enclosed areas. So if you have a graph that is both positive and negative, there is some area enclosed above the x-axis and some area enclosed below. So the interpretation of the definite integral is a net difference of enclosed areas, and we could represent it symbolically here as just a1 minus a2. Now, when it comes to evaluating a definite integral for a specific function, we're going to have to be able to take care of some summations. So with that in mind, let's recall a few of the common summation formulas that we previously introduced. If we would like to sum a constant c from I equals 1 to n, that's really just adding up c n times. So n times c. If we would like to sum I from 1 to n, that would be 1 plus 2 plus 3, adding all the way up to n. The formula is n times n plus 1 over 2. For I squared, the associated formula is n times n plus 1 times 2n plus 1 all over 6. And with I cubed, it's that same quantity from the I sum, except it's just squared. And as indicated in our previous topic, these are formulas that we should be familiar with. For this current video, our goal is to use the definition of the definite integral to evaluate the given definite integral. And let me just throw out a warning. Similar to what we encountered with differentiation, there's a definition, and eventually there'll be more of a shortcut type method. If you have previously encountered this kind of shortcut type method, maybe something called the fundamental theorem of calculus, you're going to have to hold off on using that for now. When it comes time for homework and exams, you will see questions where you are asked specifically, use the definition of the definite integral. That is going back to what we introduced in our previous discussion. And if you do not do so, you will receive very few, if any, points for the problem. So in this case, applying our definition, I will always start by just simply writing out what it tells me. So this would be the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. And to the side, let me just write out what a few of these quantities are to kind of simplify our sum and resulting limit in a moment. So delta x is b minus a over n. So a is the lower limit of integration. B is the upper limit of integration. So this would be 3 minus 1 over n, which is 2 over n. X sub I is equal to a plus I delta x. So we said a is 1 plus I delta x. So I'm going to write this as 1 plus 2I over n. F of x is the function we are integrating. So with that in mind, f of x sub I would be the quantity x sub I squared minus 6 x sub I. And as we know a formula for x sub I, let's go ahead and just substitute that in as a little bit of side work. So 1 plus 2i over n squared minus 6 times 1 plus 2i over n. If we go ahead and expand this, and I'll just do a couple steps of algebra to make sure I'm not making a silly mistake, I would have 1 plus 4i over n plus 4i squared over n squared. So think kind of just foiling that out. Minus 6 minus 12i over n. So ordering these terms from highest power to lowest power, we would have 4i squared over n squared minus 8i over n minus 5. And at this point, we've just done the sit-up portion of the problem, but things are looking awfully good. We know exactly what to substitute in for f of x sub I, and we know what to substitute in for delta x. So let's go ahead and do so. We would have the limit as n approaches infinity of the sum from I equals 1 to n, f of x sub I. So just cutting and pasting that over, 4i squared over n squared minus 8 over ni minus 5, all times 2 over n. And now is where we start doing some algebra. So let's first let the 2 over n kind of distribute through and hit each of those terms. And this is really the type of problem where it becomes important to be patient. It's just one small computation or step at a time. I find that for me personally, the more I try to do at once or mentally, the more likely I am to make a smaller, sillier mistake. So I always encourage or urge you to take your time with these problems. So just continuing on very incrementally. So distributing through the 2 over n, we would have 8 over n cubed I squared minus 16 over n squared I minus 10 over n. And what I would now like to do is note that we are adding up 3 different quantities. So let's go ahead and break this sum up over the subtractions, and while we're at it, pull out the constants. And note this is a very common technique. It's precisely what we've done many times in the past when dealing with, say, limits or differentiation. You break up over addition and subtraction, you pull out constants. So we would have 8 over n cubed, the sum from I equals 1 to n of I squared, minus 16 over n squared, the sum from I equals 1 to n of I, minus 10 over n, the sum from I equals 1 to n of 1. And the nice thing is that at this point we can apply our formulas from above. So these constants are going to remain out front, but note when we sum I equals 1 to n of I squared, we saw above that the formula for that would be n times n plus 1 times 2n plus 1 all over 6 minus 16 over n squared, the sum from I equals 1 to n of I, which is n times n plus 1 all over 2. And we also have seen that the sum from I equals 1 to n of 1, so that initial formula we had with a 1 replacing the c, is simply n. And there's certainly, simplifications that can take place here. The n over n cancels. And then looking at previous terms, you can say in the middle you have an n and one of the n's in the bottom. And in the first term, you could maybe say an n and one of those n's in the bottom. But whether we do those simplifications or not, we can really think of this as 3 separate limits. And the first 2 are limits of a rational function in n. So with our simplification, we could say degree 2 over degree 2. So we simply divide their leading coefficients. And if we do that, the leading coefficient in the top, we have to be somewhat careful, is 8 times 2 to give us 16. And in the bottom, it would be a 6. In the second term, we have what? Degree 1 over degree 1. The coefficient at the top is 16, and the leading coefficient in the bottom is 2. So minus 16 over 2. And lastly, the limit of a constant is always that constant. So 16 over 6 minus 16 halves minus 10 ends up being minus 46 thirds. And note at this point, we've done a bunch of computations. And I don't want to kind of brush that to the side, but I want to note that hopefully this all has a very familiar feel to it. It's exactly what we were doing in our previous section when we were finding enclosed areas. The key difference that we have is the interpretation. What we're getting back now is a negative. And this negative 46 thirds is representing a net difference of enclosed areas. So for this particular function, x squared minus 6x between 1 and 3, we could certainly say it encloses more area underneath the x-axis than it does above the x-axis. So I would encourage you to sketch the graph of this function, x squared minus 6x, focus in on what's happening from 1 to 3, and just ask yourself if this number or quantity makes sense. We will continue on this discussion in the next video by exploring a few additional examples. Stay tuned and take care.